Okay, so now we explain this mechanism, and the mechanism of chaos is the ARDA, transversal homoclinic points. Okay, so imagine that when you are trying to globalize the stable and the unstable manifold, yeah, you do some iterations and so on, you globalize, and then you have a point that belongs to both. This can happen in a lot of situations, but maybe the most popular is the following. This point Q belongs to the stable and unstable manifold. See that I cannot write lock because they are not locked anymore at all. So thinking the dynamics of this point is really crazy because in the future it's going to this point, but also in the past and so on. So, and moreover, imagine that you have a point that starts belongs to this stable and unstable manifold. So that means that all its orbit also is a point like this. So you don't have exactly this thing here, but you have no. Something like this, and like this, and like this, and so on. Lots of points that are homoclinic. Yeah? And sorry. So you can have this situation. For instance, when you take the time the map of our Hamiltonian system. Okay, we have here a Hamiltonian system that depends only on the space variables, and then you add some small perturbation, which is periodic in time. Yeah? Okay. So thinking this system here is a system in 3 variables. Yeah, so thinking this in this system a little bit. So you have x dot this system here, x, y, theta, e dot and here you have to think in this. I change the name because it's not exactly the time, it's almost the time. Okay. So this system is an autonomous system in R3. Yeah. So if you have you think in the map theta 0, for instance, theta t, yeah, thinking, yes, this is theta, this is x, and this is y, yes, and this is a section, this is a plane, yeah. So if you think in a initial condition here, you can think in what happens at some time t, yes, and forget about this. Because if you have any point here and thinking the time t is conjugated, you can prove that. to the same, has the same dynamics. So you can forget about what happened here and only thinking what happened going to here to here. Yeah. So this is this time t, Poincaré map, stroboscopic map, so many names. Yeah. So sorry. Imagine that you have this system. Yeah. And imagine that assume that when you don't have this perturbation, you have this situation. That is something like this. You have here a saddle. Yeah. This is a saddle. You have here a center. Since it's Hamiltonian, remember that we only need to check that this is a linear center. Okay, something like this. And this is a really natural situation to have for Hamiltonian systems. Yeah? And now think what happened when you take epsilon, sorry, different from zero. Yeah? So things will be more or less like this, but not exactly like this. Yeah. So the stable manifold is going to be closed. The other one is going to be closed. So things that are close to course can met. Yeah. Yes. And in fact, in this case, we have a method to detect the distance to detect if the manifolds intersect. This is a nonlinear. I don't write anything, but just to let you know that we have some method in this case to see if these manifolds meet or not. Okay. So the situation of having these transversal homoclinic points is, at least in this case, more or less generic. And for area preserving maps, it's also generic. So you encounter this situation. Okay. So think now that you have this homoclinic point. Let's see what. So imagine then that you have sorry, I explain what means homoclinic. That is that to have to be in the both in stable and unstable, and transversal is that the intersection is not tangent. Okay? So now think in what happened here. The thing that happened here is that it appears this is called name. Okay. And let me say which is the structure we have in the section. Yeah, and see why is it. This is made a horseshoe. We see if I can. House. I mean, you can prove analytically, mathematically, that any condition of the deterministic cause is satisfied. Okay. So, which is this small horseshoe, and how we can have this structure in this heteroclinic homoclinic intersection. So imagine that you have this stable and unstable. This you have this one of blue and red. Okay, and take here a neighborhood. I need colors. Okay, so imagine that you have this here. Yes, whatever. Yes. Hostia. A buenas horas. Qué mal. Hostia, tú. Será eso. Okay. So, thank you. Imagine that you have this this intersection, this homoclinic point. You have this neighborhood, and then it is clear that since these points belong to the unstable manifold, you can take this neighborhood here, and at some point, some iterates of these neighborhoods will be arrived to Q. Yes. So we have some iterates. I don't care in this part, but we have something like this. Yes. And this will be this, if this neighborhood is A, this will be Fn of A. Yeah. And then take, by the unstable manifold, take some negative iterates of this point, and then we will have something like this. Yeah. This will be F minus M of A. Yes. Take anything that doesn't matter here, and then we have something like this. Yeah. Which is our basis, just to say. And then if we take this part here, iterating M plus N times, we get the red zone. Yeah. And the red zone, sorry, is something like this. Yes. So imagine that this picture is okay. Yes. So now take the part in this light color, violet color or whatever. Yes. So this is this part here. Yeah. Say this B. And take F of M plus N of B. Yes. And then you have your. Okay. So the function, so the map that so we have some map. Okay. So you have this structure that you have this set with the image have some self-intersection. Okay. And this is the only thing that you need to use all the theory of the Smith-Horseshoe that I am going to explain now. Yes. So when you have here, when you have a homoclinic point, you always can do this construction and see that you have this structure here. Okay, this is true. Now we are going to see what means, what kind of results have when we have something like this. Okay. Yes. Yes. So now Smith-Horseshoe. Okay. So now I need to see this. Okay. So this is a toy model. A toy model of this situation here that happens when you have this homoclinic. So, and the top model is this one. So imagine that you have a square, D, and you make the following transformation. You shrink in the horizontal. So this is 1. This is 1/3. Okay? This. And after that, you bend just, let me write here, D. You put this part above in here. Yeah? And then you bend. Yes? And then you have something. Okay? That's it. This is the horseshoe map. Okay? So see what happened, for instance, if you have something here. This will be H1. It will be H0. Okay. Yeah. What happened here is that this red part is going here, the purple here, and then here and here. Okay. So if you call this map F, for instance, full map is F, we have that the image of H0 is this B0. So horizontal strip is going to a vertical strip, and the same for B1.
What's the part of the top?
This part.
This one is 1/3 and 3. So we just put them.
Yes.
Okay. Keep the area, but
the thing is that you can think in this system, so you can make, is it more or less like the logistic map? Do you remember the logistic map when mu is more than 4? Okay, so what you have is something, yes. So everything here is going out of your definition domain. Yeah, so here we have the same. So this part in here is going here, and this part is going here. And the other part, of course, it belongs to R2, but it not belong to the square. Yes? Okay, so we have this. Now think in doing another iteration. Yes? So if we think in one more iteration, okay? Now what we have? We will have, see what happens when we shrink now. Okay, so we have to have the memory of this part here. Yes. So here we will have something like this, maybe later, and something like this. Yes. Okay. And now we put this figure, yes, in the square by bending this strip. Yeah? So this part again comes to something in here, this B0, yeah. But now we have this part, sorry, and this part here. Yeah. And then we have this one. Does also have a part of this vertical strip, but I don't care because it's outside of my domain. And then, since we are going to do this in this part, then what we have is something purple here and red here. Okay. Again, what we will have? Then instead of, so here we have 1, 2, another time we will have 4, and so on. Yes? So if we do the same another time, what we will have is nothing but 4 rectangles in any part of this D here. Okay? So now Thomas did my work. Think in the set of points that always stay in D. Yes? So it is clear that in here we have some points that stay forwards, always in D. Yeah? We ask about this, this set. And we will do the same for the inverse. And then we will have an invariant. Okay? So the thing is how this invariant is. Yes? So now think, for instance, in, let me do it again. Yeah? Again, another iteration. This is F. This is, sorry, this is F squared. So another iteration, just we'll do something. Well, now I don't have, I need to do things because if not, I will be wrong. So another time, again, this. Red, Julians, pardon. I've broken any time. This one and this one. Okay. And then the squares. Okay. And then bend again. If you bend again, what you have is one red in here, one purple, sorry, red and red. Yes? And so on. Okay? So now we are thinking in the set of points such that stay in D for any iteration n. Yes, backwards and forwards. Okay, so it is clear that, see, for instance, what happened. No? If you have a point here, it means that by the inverse, stay in the set. Here, if you have a point in these two rectangles, it means that by the F power minus 2 stay in the and so on. So if you have a point in here, means that f minus 3 of p, f minus 2 of p, f minus of p, and p belongs to D. Yes? So here, in this set, is the set of invariant points by f minus. Yes? Backwards. And see that, sorry, we see here this H0, H1, we can say B0, B1, yes, 2. But now we have this one here, yes? So we say, okay, this point, this rectangle will be B, because it's a vertical. 0, because belongs to 0, yeah? This is 0, this is 1, belongs to 0, and comes from a 0, because comes from here, yeah? So see that if you have a point in this B0, 0, that means that P belongs to B0, but the anti-image also belongs to B0. True? So now think in this one. B. This point belongs to 0, yes, but comes from B1. So 1. Yeah? Here the same. This belongs to 1 and comes to 1. Yes? And here 1, 0. Yes? It's a way to label all these rectangles. So in the same way that you here say, okay, B0, B1, here you say, no, I need 2 symbols here. So I say 0, 0, 0, 1, 4. Yes, it's the same. It's a way to label. And now we do the same in the other part. In here, yes. So in here, we have this part here, is this part. Yeah, this part comes from B0, 0. Yes, so it's B0, 0, there, 0. The first one is the way where we are, yes. This here comes from this one, which is B0, 1, 0. This part comes from there, which is B0, 1, 0, because it's 0. And this part here comes from, sorry. No. B1, 1. Yeah? Okay. And the red part is B1, 0, B1, 0, 0. Okay? And the same for these ones. These ones are B0, 0, 1. B1, 0, 1. B1, 1. All the ones. B1, 1. Okay? This one? This one is, yes, B001. Okay? And so on. Yes? So in this way, see that if you do this at any step, yeah, doing any times, we have lots of rectangles, yeah. Any of these rectangles are labeled for n chains of ones and zeros. So you will have, and I write this. This is not really important, but yes, this one are zeros and ones, and tell you the travel that the points in this rectangle has done to get there. No? So these points means that the point belongs to this sorry, I need words, to this vertical strip. That means that the point applied the inverse belongs to this one, the 2 inverse belongs to this one, and so on. Yes? So the thing here is that we have that any point that belongs to these strips satisfies that P, f of P belongs to f of S. Just to write what I was saying. Yes? Okay, so now think not in this map, but in the inverse. Okay? The inverse map. Well, the inverse. It's not the inverse, but it's a sort of inverse. It's the inverse in the image. Okay? So the inverse map, I have to, sorry, is there? It's because I never remember if, yes. Yes. No, it's the composition. Is that here you always have a minus. If you want, I think that this is also correct. Yes. Yes. Yeah. No. Yeah. Yes, because the thing is that even when you are doing image, then the points that belongs here, the characterization is that the anti-image belongs to something. Yeah. So so the inverse map is as an small horseshoe, of course, and is just a range in this horizontal direction and then bent like this. And here, the important thing is that you have here this B0 and B1. Remember that are the image of the horizontals. And then you have here B0, and then you have here B1. And then here you have that the image of this one is going down. Yeah, and the image of the up is going up. So here you have this AJ. The same situation as before. Okay. And this is an inverse in the vertical strips P0, B1. Okay, which are the only ones that we have, we can do the inverse. Okay. And now think that we are doing exactly the same that we did for the small horseshoe, we do for the inverse. Okay, so the situation is symmetrical with respect to horizontal and vertical. Yeah, so now in here we have verticals, and in the first we have horizontals. Here we have horizontals, and then we have verticals. So what we will have is a sort of vertical strips labeled by something. I put a 0, but we will see. Satisfying the same property. The same property is that P belongs to here if and only if the image J of P belongs to H is J. Okay, same. Yeah. We have always this discussion with F, with H and B, but don't care. Seriously, it's this is okay, and this is not the important thing. The important thing is that the invariant set, so the set of points that stays always in the future and in the past of this Smith horseshoe, is labeled by sequence of zeros and one in the past and in the future. So for any point in the invariant set, we have an invariant sequence, an infinite sequence, sorry. Yes? You agree with me? So see that here. See now in this, in the set, the set of points in the future. Is can be identified by simply sequence of zeros and ones. No? Here, the ones that we did by using the Smith horseshoe, and here the ones that we use, we obtain using the inverse of the Smith horseshoe. Okay? Yes. And see, and now I am going to kill you more. And I'm sorry, but this is difficult. So think now, sorry, in this the set of points, but this set of points, let me say gamma. So imagine that you have a point that belongs to gamma. Yeah. Because this set is invariant, and this is true. But when we have a set that is invariant, we need to know the dynamics on it, how acts the map on it. If not, we don't have any information. Yes. So now we want to know which is f of p. Yeah. So if we have a point in this invariant set, we have this sequence. So the only thing that we need to know is what sequence corresponds to the image. Yeah? So what is the sequence that corresponds to the image? And this is not so hard to do, because think that if you have a point that belongs to this set, then we have something like this. If you have the image, well, so you have the image. Yeah. This is yeah. So the only thing that we need to do is just to shift the index. Yeah. So this is the position J. Sorry. Yeah, and corresponds to one more. So what we have is something like this point here is just one step. No?
Okay. Okay, so the conclusion here is that subtract point. I mean, it's not a numerical equation, it's not. Okay, so, hang on. Any question?